Hi, Anaya.
Hello.
How are you?
I'm good. How are you?
I'm good. Doing good. We have we have a helper with us today.
Oh,
We'll see how he does. He might lose it. We'll see. You want to go to sleep for us, Bubba? Yeah. Well, y'all doing all right? We've got Aaliyah and Elia. Those names are very similar. Aaliyah and Elia.
What's his name?
Joel. That's my son. Name is Joel. You want to say hi, Joel? You say hi to everybody. You just gonna eat your fingers? No. Hey, Bubba.
Hi, baby.
You wanna say hi? You were just saying hi. Not sure about it? Okay. We'll come back. Hello, Kathleen. Hey, Zoe. I'm not sure how many people are gonna join us, but yeah, pretty much this is just for the lab. If you have questions with the lab, if you have questions, there he is. If you have questions with the homework, here for you guys. So I imagine we won't go more than 45 minutes or so, but I'll be here as long as there's questions. So anybody want to take the first question or have a question?
is there any way you can like view quiz 7?
Yes.
I think it was question 5.
Yes.
I got like the 2 parts of it, but trying to figure out what the whole question was asking, I
Okay.
couldn't figure it out. Like my numbers didn't match.
And we'll just go to, all right, I have it right here. So I wanted you to calculate delta G, all right? And
It was the one with delta H, I think.
oh, calculating delta H.
Yes.
Here it is. And number 3. Let me minimize this a little bit. So the question says, I'm just going to share my screen and pull up a blank note here, and we'll just work this one.
Okay.
Okay. So the question on this one says, use the table of bond dissociation energies below, calculate delta H for the following reaction. Now, I will say this. If you were one of the first people to take the quiz, like very early in the morning, there was actually a typo in this. And I announced that to the morning lecture. I did not take the time to announce it to the afternoon lecture because it had already been fixed. So I did not have the correct answer listed. And if you were one of like the first 8 or so people to take it, I went in and it updated your grade for you. So here's how you should have worked it. We had nitrogen N2 plus 3Cl2 making 2 NCl3. All right, we're going to calculate delta H. So we always know we have to have, look our equation. Hey, buddy. Looks like our equation is balanced. And we need to now draw out Lewis structures for each of these. So we're going to have nitrogen molecule, which is a triple bond. 2 nitrogen atoms triple bonded. We're going to have a chlorine molecule. That's a single bond, 3 lone pairs each. And we've got 3 of those. So we'll take that into account when we calculate this. 3 chlorine single bonds. NCl3 looks just like ammonia, which is NH3. It's just that these atoms are chlorine. Can y'all hear him?
He's so sweet.
He is a sweetie. He's talking a lot these days, which is awesome. Okay, so we've got 3 nitrogen chlorine single bonds as well. And we've got 2 of these molecules. So I have to take that into account when we calculate this. So we're first going to calculate enthalpy of the reactants. And then we'll calculate enthalpy of the products and we'll subtract the two. So to do this, we needed to find, first off, if we're looking at nitrogen, what kind of bond do we have here? We have a nitrogen triple bond. And we just have one molecule. So the number for that is 226. You are really talking. All right, and we're just multiply it by 1. So that is the nitrogen triple bond. That takes care of that. And we have a chlorine-chlorine single bond, which is, if I look at the table, here's where I messed up. I put in when I calculated this myself, I put in 81 instead of 58, but they're right by each other if you're looking at that table. I calculated with the value of carbon-chlorine single bond. It should be a chlorine-chlorine single bond. So it should be 58 kcal per mole. And we've got 3 of these. So we're going to multiply that by 3. Everybody with me so far? Okay. If you just joined on, we're working number 3 from the quiz, the one where you calculate delta H. Okay, so total, you should have 226 plus 58 times, I'm trying to yell over him. 58 times 3, 174 plus 226. The total for enthalpy of the reactant should have been 400 kcal per mole. Okay. Then for the products, so this is going to be enthalpy of the products. You've got in one molecule, we've got, I'm going to number them, 1, 2, 3 nitrogen, chlorine, single bonds. But we have 2 molecules. So total, how many is that?
Is it 6?
Yep. So we'll do 6 times the nitrogen chlorine single bond, which is 48 kcal per mole. Okay. So 6 times 48, double check me. I got 288 kcal per mole.
How did you get 6?
The number of bonds. So we have 2 of these molecules, that coefficient of 2. So that would be like me copying and.
I got you. I got you.
Now if you count up all those individual bonds, you should count 6.
That's where I messed up at. Yeah.
That will get you. So now if you do 400 minus the 288, you should get 112 kcal per mole. So that was the quiz, or one question on the quiz. Multiple choice number 3.
Thank you.
Yes. Any other questions from the quiz? Did you guys do okay with that last one, calculating delta G?
I felt confident because my answer was on the multiple choice, but I got the wrong one, and I don't know if I actually did it correct.
Oh no. So that one, all you had to do was convert the temperature to Kelvin, and then you just you should have converted your delta S to kcal and then just plug it all in. You should have got 23.06 kcal. I think the correct answers are visible now on the quiz.
Yeah, I originally got that 19,000 something, and I was like, that looks so wrong. And I was like, oh, I didn't convert it to kcal.
Well, here's what I'll do. I'll put answers on there specifically for those mistakes. I'll say, what mistakes are they going to make? I bet they're going to forget to convert their temperature, and I'll do it with, the Celsius temperature. I'll put that answer on there. I'm baiting you guys.
I must have forgot to do the kcal because I got the negative 19 something.
Oh, yeah. You would end up subtracting by a way, way, way bigger number if you forget to convert to kcal.
My bad.
So, any other questions? Quiz, homework related, dry lab related?
I have one about the homework. It's number 32.
You know what I went ahead and pulled up because I knew we'd get questions? Okay, is it problem 7.77?
Yes, ma'am.
I swear he is never this talkative. Okay, so this problem, just gonna look at it for a second. It says how much heat in kilocalories? Pull my screen back up. How much heat in kilocalories is evolved or absorbed in the reaction? Evolved is a fancy word for produced. So produced or absorbed in the reaction of M of Na. What is M of Na? With H here, let me look at it in the standard view. Okay, let me read it now. Okay, how much heat in kilocalories is evolved or absorbed in the reaction of 2.03 grams of sodium with water? So your numbers may be different. Sometimes mastering gives different numbers, but essentially here's what we have. We have the reaction of this 2 atoms of sodium plus 2H2O, it's a liquid, and we're gonna make 2NaOH aqueous plus H2, and that is a gas. And your delta H, it gives you delta H for the equation, and it says that is negative 88.0 kcal, and it gives you kilojoules as well. We'll come back to that if we need it. So if we have 2.03, it says, this is the number at least the problem gives me, grams of sodium. It says how much heat in kilocalories is evolved or absorbed. Well, we know delta H is negative here. So this is an exothermic reaction. So overall heat's being produced, or we could use their word, evolved. So we need a relationship between delta H and here, sodium. So if I wanted to write this into the equation, I could write, I need to shrink this down a little bit. I could write plus 88 kcals on this side because we know it's a product. And let me try to give him a passy real quick. Is this what you want? You want to take that? No, you don't want it. You think about it, okay? All right, so looking at the balanced chemical reaction, you can always do this for any reactant or any product. We're gonna write one for sodium. So we have, for every 2 moles of sodium that we put in the equation, we are gonna get out 88 kcals of energy. So I'm just gonna write that as a relationship. For every 2 moles of sodium, we're gonna get out 88 kcals of energy. That's the relationship. Now you're gonna plug this in as a conversion factor. But I believe here when you write it, we forgot the negative. When you plug it in the equation, you don't need the negative, but when you write this relationship, you need to use the exact value of your delta H. So don't forget that negative here, or we'll get the wrong answer. Now it gives you, can you let me make it through this one problem? And then I'll get you. It gives you 2.03 grams. So to use this relationship, we first have to convert grams to moles, okay? And you guys know how to do that. We don't even have to calculate a molar mass here. We just look at the periodic table. Okay, we're gonna look at the periodic table. What is the mass for sodium?
22.990.
22.99 that's grams per 1 mole of sodium. Now we can plug in our mole to kcal relationship. We want to cancel moles of sodium, convert to kcals, okay? And if you forget your coefficient here, that will mess you up as well.
I think that's where I went wrong.
Forgetting your coefficient?
Yeah, I put 1 instead of 2.
Okay. So you'll notice grams cancel, moles of sodium cancel. I think there's several problems on the homework where you do stuff like this. I've gotten questions about another one as well from emails.
Okay, so where did you get the 2.03 from?
That's just what my problem gave me on part A. This
Okay.
is 7.77. It may start you out with a different number of grams.
Yeah,
Okay.
mine is,
Told me 2.03. So whatever it gives you, you need to plug in where I put the 2.03.
Gotcha.
Yeah. There you go. You want that? Okay, maybe we're good. All right, any other questions?
It's not like specific to like, because I'm be honest, I haven't looked at the homework yet. I'm gonna do it, but I just haven't looked at it. Can we like do more problems like related to like change in empathy and like the delta G and stuff? Because like a lot of times I'm just confused on like where you're getting those numbers from.
Taking delta H and delta S and plugging them into delta G, that's what you want?
Like, yes, but like really more of, okay, because looking back at my notes, like really like questions like on the lab. Like, I'm not saying we have to like work questions directly to the lab, but like questions like that, because I
Calculating
just get
delta H.
confused.
Yeah. Well, here's what we'll do. I actually have some we didn't get to. I said, remember, we can use these as review, but that'd be great to look at right now. So if you have your lecture notes, pull those up from chapter 7. And right before we get to the enthalpy slides, there are 2 slides that sit, or sorry, right before the entropy slides, there are 2 enthalpy slides of problems that we did not work. So can y'all see these on my screen?
yes.
Hey, bud, I gotta work another problem, okay? You have that. So we're gonna work this first one. It says for an endothermic reaction, well, actually the second part is what you're asking, but let's look at the first part real quick. For an endothermic reaction, is the total enthalpy of the reactants greater or less than total enthalpy of the products? So what does endothermic mean? Delta H is positive or negative overall?
Positive.
Positive. For endothermic, delta H is a positive number. Okay, actually I want to write it on the other side, sorry. I want to write it right here. So if it's positive, do you know the equation for delta H? Delta H equals what? How do we calculate it? Delta H is enthalpy of the reactants minus the enthalpy of the products. Okay, so to get a positive number over here, because we're inherently subtracting, which number has to be bigger?
The reactants.
Enthalpy of the reactants. This has to be, essentially what we're saying is enthalpy of the reactants has to be greater than enthalpy of the products. That's the only way you get a positive number. Because we know bond dissociation energies are all positive numbers. Okay, we don't have any negative. If I scroll up to that table with all the different bond dissociation, they're all positive. So if we're plugging in positive numbers into our equation, but we're subtracting numbers, then this first one has to be bigger. For example, that's like saying, just if we plug in a simple whole numbers, if this is 100 minus 200, we know we're going to get a negative number if enthalpy of the products is bigger. But if we're going to get a positive number, it must be that the opposite is true. We have a bigger number here and a smaller number on the product side. That gives us a positive number overall. Okay. All right. But the second part is actually what Kanithia was asking about. It says estimate delta H in kcal per mole for the reaction of hydrogen and oxygen to form water. So take a second and go ahead and write out the equation. Hydrogen and oxygen to form water. Kanithia, you did not remind me to record this. Did I have this set up to automatically?
It was already recorded, and that's why I didn't say anything.
Okay, good. Thank you. Also, I don't have my chat up. I'm very sorry if you've been chatting me. Oh, Brennan just said, "Oh." All right, so who's got our reaction for us?
I thought I had it, but this doesn't look right.
What do you
Got
have?
2H2 plus O2 makes 2H2O.
Okay, so Kathleen says she has H2 and she's got 2 of those. Remember, hydrogen is a diatomic plus oxygen, which is also a diatomic. We've got 2 oxygen atoms on the reactant side, and we've got 2 now on the product side. All right, now we need to draw Lewis structures. So step 1 is always get the balanced chemical reaction. Step 2 is draw Lewis structures. Step 3 is find your bond dissociation energies and plug those in. So hydrogen is just going to look like this. I'm taking less time to explain Lewis structures here since we spent all that time in chapter 4 on them. All right, oxygen should look like this, a double bond. So if you are iffy on Lewis structures, go spend some time there. So water looks like. Okay. So now we need bond dissociation energy values. So let's do the enthalpy of the reactants first. I like to put it all in big brackets. We have a hydrogen-hydrogen single bond. And we have how many? We have 2 of them. 1 in each molecule. In total, we have 2 molecules. So that is right here. The value is 103 kcal per mole. So you're going to do 2 times 103 kcal per mole. We're going to add to that, because we still have another reactant. What kind of bond do we have in oxygen? Here's where people get confused. This is one, right. This is 1 double bond. This is not 2 bonds. This is one, the kind of bond it is a double bond. So we're going to treat it as 1 double bond. And we only have a coefficient of 1 here. So we don't have to multiply anything. So the value for oxygen, an oxygen-oxygen double bond, that's what we need. I'm going to go to the table. There it is right there, 119. So you're going to also add that to the side enthalpy of the reactants. Okay. He's looking at me like, what are you doing to me? On the product side, so we're going to subtract this off in a minute. We have a water molecule. What kind of bonds do we have in the water molecule?
Single?
Yes, and it involves a hydrogen and an oxygen atom. So we have a hydrogen-oxygen single bond. And so let's just go grab the value for that really quick, and then we'll see how many we need to multiply by. hydrogen, oxygen, single bond, hydrogen, oxygen, single bond. So right below our hydrogen, hydrogen. So 112. So we're going to do 112 kcal. And we need to multiply it by the number of bonds that are going to be formed here. How many oxygen, hydrogen, single bonds are going to be formed from this balanced chemical reaction total?
2? Or is it 4?
Is it 2 or 4? What do y'all think?
I think
Brittany
it's
said 4. Aaliyah said 4. Okay, I agree with you. It's 4 because we've got 1, 2 in one individual molecule, but how many molecules do we have? We've got 2 of them. So that would be like me saying, oh, whoops. Copy. So we've got this. Now you can count them all visually. There's 4 there. There's the third one. There's the fourth one. I'm going to do times 4. So now let's add everything up. On the reactant side, you've got 206 plus 119, that's 306, 325. Is that right?
Yes.
Okay. On the product side, 112 times 4 should be 448. And we're just going to subtract those two numbers. So your delta H equals 325 minus 448, which total gives you 123. So,
Negative 123.
yes, sorry. Thank you, Dakota. Negative 123. Yes. Yep, Aaliyah got it. Okay, was that helpful, Kanithia?
Yes. Okay. So if it's a diatomic, we don't do for instance, hydrogen, we wouldn't do 2 times 2. We just go off of the coefficient.
Well, you have to draw out the molecule. That's why I think drawing the Lewis structure is critical here. And when you draw it, you see there's 2 hydrogen atoms, but this 2 right here, that's not telling you the number of bonds in the molecule. That's telling you how many atoms are in the molecule. Because there's only 2 atoms, they're connected by 1 bond. But it's different for every molecule. An oxygen molecule, there's 2 atoms, but they're connected by a double bond. So you have to see, what kind of bond do I have? Do I have a double bond, a triple bond, a single bond? What atoms are involved in that bond? Just because there's a 2 here and there's a 2 here does not mean we have 4 bonds. That means we have 4 hydrogen atoms total. Okay, it means we have this. Okay, now you see all 4 atoms. But those 4 atoms are arranged into 2 molecules. Each molecule has 1 bond. Does that make sense? I
Yes,
can
it
tell your
does.
face when you're confident and when you're not.
It's just, okay, so just because oxygen is a double bond, that just counts as just technically 1 bond then? I feel like this is just relating back to Lewis structures.
It's
And
it's
I'm just-
1 double bond. 1 double
Okay.
bond is 2 individual bonds, but we don't treat it like 2 separate bonds because we have the value on the table directly for a double bond.
Okay. Okay, I think I got it. I think it's clicking now.
Okay. If you want even more practice, right below that is another one. You've got this I'm on erase. So you've got this reaction here, and you can write and estimate delta H for that one as well, for good practice. And we'll do it before the exam. Any other questions from the homework or the dry lab or?
I
On the,
have
ho-
Oh, you can go ahead.
on the homework, on the last question, are we drawing the Lewis structures first? Is that what that box is for?
Yeah, and so that's giving
Okay.
so many people headaches. I actually have the Lewis structure for NO2 drawn out for you on the dry lab, remember? Number 4. That Lewis structure is right there. Everybody keeps messing up, and here's why. On NO2, they put a lone pair on NO2, but if you look at that structure, I don't have the lab right here to show you. There's a single lone electron on the nitrogen for NO2 because there's actually charges within this molecule. The nitrogen has a plus charge and the oxygen that has 3 lone pairs has a minus charge. So make sure when you draw that, don't accidentally put a lone pair on nitrogen, just put a single lone electron when you draw those Lewis structures out on that homework problem. And you don't have to draw like multiple, you just need to draw one molecule each.
Okay, yeah, that was confusing me because it didn't really exactly say how they wanted it.
I had a question, but mine was something like about the quiz.
Uh-huh.
I don't, we don't know what we missed, but I was gonna ask you like maybe what was one of the most missed questions since you probably can't remember directly what I
Wait, you
missed.
can't see what you missed?
No, ma'am. It just shows me like, cause you go back to the submission, it just shows you the score.
Let me see if that's not how I intended it to be. 2 seconds.
Hey, Brennan,
Yes.
do you have your Blackboard pulled up?
Yeah, I can for sure. Especially if you're gonna help me for sure.
Okay, if you click on quiz 7 and it says your score, it should be in purplish or blue, and then you click on the score, and that's how you
Wait.
can check your.
Well, see, like when I did that, cause I tried to do that. Let me try it again. But when I tried to do it the first time, like it only showed me like your test had been submitted and like your teacher knows that it's submitted, and that was it. So
Did
let
you
me
try to check it before 11:59?
I
Yes.
so it probably was. It probably was because I did the quiz before.
Okay, so now you should be able to see. So here's the deal, and this is how from now on I've learned, because remember when I used to always be like, no, you can see it, and you never actually did. I'm the biggest idiot ever. I've learned now, I've checked all the boxes. So if I could share my screen, it stopped sharing with you. If I could share my screen with you and you could see, I have all of I have everything checked. So after the due date is when the answers show up. So if you submit yours and then go try to see the right answers, you can't. And here's why. Because other people probably still have not taken the quiz yet. And I just don't want answers to be shared, obviously. So once everybody turns it in, once the due date has passed, 11:59, then you can get on and see the correct answers. Does that help? Maybe if you try it now, maybe you can see it.
Yes, I can see everything now. It makes a lot of sense. I'm kind of like in a off factor.
That's okay. Do you have a question from that, Brennan?
Yes, I'm actually gonna try to pull one real quick.
Okay.
Like, let me see. Something that just really kind of threw me. Maybe the last one, number 6. It wouldn't hurt to practice that one. It was with the well, I
Delta
thought I
G?
got that one. It was it was with Delta G, but all you're doing is plugging it in, so I don't.
Well, you first have to do 2 things.
Mm.
You have to convert your temperature to Kelvin,
Right. Oh, that's what I didn't do.
and you have to convert delta S to kcals.
Okay,
There's 2 steps there.
that's what I didn't
When
do.
we worked it in the lecture, I said, remember these 2 steps. You gotta do both of them. Where did your pen
I think I assumed. Well, that one's not based off of bonds. I don't know what. Maybe I made it just.
Okay, you don't have to draw anything out or look at bonds here. Here, you just take the 226.85 degrees Celsius temperature. You can
Set it
Kelvin.
up in the
Nice
chart.
around 500. And then you plug in the 42.3 kcal and you plug in minus the temperature times the delta S. So when you do delta S, when you convert it to kcal, you just take 38.48 divided by 1,000. You okay, buddy? So 38.48 divided by 1,000, you should get 0.03848. Here, I'll just work this one real quick. I already am halfway.
I get what you're saying though. I should have that probably would have adjusted my calculations because I did not convert it.
For sure, it would have adjusted your calculations. So you had delta G equals, our delta H is 42.3 kcal minus, and so the temperature conversion is this, it's 226.85 plus 273.15, and you should get 500 Kelvin. And then the conversion for delta S is 38.48 calories per mole Kelvin. And we're going to divide this by 1,000. We're going to convert to kcal. So we know there's 1,000 calories in 1 kcal. So calories will cancel and you'll get 0.03848. Now your units are kcals per mole Kelvin. No, you don't want it. Come on. Now you can plug everything in. 500 Kelvin minus 0.03848 kcal per mole Kelvin. Now, if you do that, you should get 23.06 for your delta G. It should be positive. So you should get a 19.24 kcal per mole here. Your kelvins cancel. So you do 42.3 minus the 19.24. Bubba, you tired. Here you go. So that was the last one. Are there any other questions on the quiz?
Yes, I had a question.
James.
So for the quiz, the only one I missed was the first one, which dealt with what's a favorable reaction and what's not. And what confused me is, well, the way I think about it, when the products have the energy, like the kinetic energy, right?
Potential.
Potential.
Yeah, we're talking. So potential energy is stored energy, and when you're dealing with chemicals, you have stored energy in the bonds.
Okay. So for me, what I chose was A, which is the products have more potential energy than the reactants, and that was wrong. So.
Okay, so it should have been, yeah, B and D. So the products, when what's favorable is when you have a negative delta H and a positive delta S. That gives you a favorable reaction always. So if you got the delta S part, that disorder is increasing, that corresponded to answer choice D. So that is definitely corresponds to a favorable reaction. A and B, the products have more potential energy or less potential energy. This is with regards to enthalpy. Okay. Come on, dude. I'll be done in just a minute. All right. So if we have a negative delta H, we know that delta H equals enthalpy of the reactants minus enthalpy of the products. So for this number to be negative, enthalpy of the reactants or enthalpy of the products, which one is bigger?
The products.
That's right. Sorry, guys. Hold on. Hey, Bubba, you're okay. You're okay. There you go. There you go. Okay, enthalpy of the products is bigger. That's correct. Now, here's the deal you have to remember. I'm going to go back to the slide that I'm thinking about. This was chapter 7 slides right here. We filled these two things out. We said breaking bonds requires energy and making bonds releases energy. So think about that. When you're making bonds, which corresponds to your product side, you're releasing energy. If overall you're releasing more energy than you're absorbing, then the products are going to have less energy, because when you make bonds, you release energy, you give away energy. That's why the products are going to have less potential energy, because if your delta H is negative, you have given off more energy than you've absorbed. So overall, you have less energy, and that means you're more stable. Does that click at all?
So for an exothermic reaction, which side would you write like the plus energy on?
You would write it on the product side, but
that's
that
what
doesn't mean the
confused me.
product that doesn't mean, James, that the products have that energy. Okay, so let's just look at this. So we have A, B makes A plus B, and if this is an exothermic reaction, we're going to write plus energy. That does not mean that the products have that energy. That means energy is another product. That means they have given off more energy.
Okay.
That I see how that can be confusing, but that doesn't mean these products have this energy. That means that we're giving away energy. So these are left with less energy.
Okay.
That's probably where you got tripped up.
I have a question about the homework. It's it's number 1.
What is it on the homework?
Yes, ma'am.
Okay, hold
The
on.
boxes, all mine are bunched together, so I don't know what they say.
He's just gonna join us. Which one is it?
Number 1.
Okay. Number 1.
Is it the one where you have to sort them into the different boxes?
Yes.
I know if you if you pick it up and you drag it away from like the other boxes, it'll tell you what is in it. Because I had that problem as well. I think if you try to drag it like somewhere else, it'll like.
Oh, I see it.
Yeah, it won't overlap with the other ones.
Oh, okay. Thank you.
You're welcome.
The text all looks overlapped. Is that it?
Yes.
I see what you're saying. So you can't even read the box.
You just have to drag it away from the other boxes to read it.
Oh, wow. It must be glitched or something. So yeah, if you drag it away, you can now see glucose and ATP give you glucose 6-phosphate and ATP, and then it shows you what the K is. Yeah, so here you're looking at the K, the value of it, and then you're saying, are the products or the reactants favored? And to answer that, you need to make sure you finish watching my equilibrium video that I posted this morning. That'll help clarify. But I'll give you a quick note. Y'all can still see my screen, right? If K is greater than 1, I don't care how big, okay? If it's just like if K is equal to 5, or if K is equal to 5 times 10 to the power of 30. No matter how big K is, if it's bigger than 1, your products are favored. Okay. And then vice versa. Ow. If K is less than 1, and I don't care how small, if it's like barely less than 1 or a whole lot less than 1, your reactants are favored. Okay. So I'm trying to pull the chat up because I saw somebody type something. Okay. Does that help?
Yes, ma'am.
Good deal. Any other questions?
Do you think you could, I did part 1 of the dry lab. I just want to know if I did it correctly. So is there a way like you could just do a walkthrough? Because
Right here. Part 1. Let me erase. Okay, part 1 says you have carbon tetrachloride and hydrogen can be formed by reacting methane and chlorine. So what do you have for your balanced chemical reaction, Aaliyah?
I have CH4 plus 2 Cl2 arrow CdCl4 plus 2 H2.
Okay, great. That looks balanced. So then we should write out Lewis structures. Okay. So for carbon tetrahydride, you got your carbon and you got your 4 hydrogens put around it.
Mm-hmm.
No lone pairs.
Mm-hmm.
For chlorine, I can't remember if we drew this earlier or not. I knew we drew oxygen.
Are you writing right now?
Can you see my screen?
But I couldn't see what you're writing or anything.
Oh, it has glitched. Yeah, I erased everything and started writing this one out. Let me reshare. Okay, now can you see it? You just want to join us, Bubba? Oh, I'm not on my pencil. Okay. So there's the chlorine molecule.
Mm-hmm.
And for the product side, you've got your carbon with your 4 chlorines. Excuse you. And those have a bunch of lone pairs on them.
Mm-hmm.
And then the hydrogen molecule looks like that. So there's your Lewis structures.
Mm-hmm.
So then you add up your enthalpy of your reactants and your enthalpy of your products.
Yep.
So what do you have for that side?
For that side, after adding everything up, I had 512 kcal per mole.
Okay. But when you actually look at what kind of bonds you had, you did the number, the bond dissociation energy for carbon-hydrogen bond. You have a single bond there, and you've got 4 of those. So you should have done 4 times the bond dissociation energy for that.
Uh-huh.
And then you add to that, we've got a chlorine molecule, but we have 2 of them.
Mm-hmm.
You add 2 times the bond dissociation energy for that chlorine-chlorine single bond.
Yep.
And that should, I'm guessing, gives you 512.
Yep.
Then you subtract off, you have a carbon-chlorine bond,
Mm-hmm.
and you've got 4 of them. So you do 4 times the bond dissociation energy for your carbon-chlorine bond. Plus, you add to that, I need to shrink all this down. The hydrogen-hydrogen bond, and you've got 2 of those.
Mm-hmm.
2 times the bond dissociation energy for hydrogen-hydrogen single bond.
Yep.
So if you did all that, I'm going to guess that you did it correct. What did you get for your overall delta H?
So my question was, at the end when you get those, is it the 512 kcal mole and then it's minus the products?
Yes, so what, I don't know what you got on your product side, but
530 kcal over mole, and I got negative 18 kcal per mole.
that
And
sounds right to me. Anybody remember doing this one? Negative 18?
I got the same answer.
okay, great. I was just making sure like I was doing everything
Yeah,
correctly.
and when you type it into Blackboard, you'll type negative 18 and then kcal/mol.
Okay.
When you type in your delta H's, it's kcal/mol. Okay,
Mhm.
Yeah.
Alrighty, cool. I was just making sure I was on the right track with that.
you bet. Any other questions?
I've got a homework question.
Okay, what's up,
I'm
Kathleen?
I'm on number 10. It's problem 7.30.
Number 10, problem 7.30. I'm gonna pull that up. Number 10, 7.30. Here it is. Oh, someone else was asking about this. This one's the part with A, B, C, D, E, right?
Yeah, I've got it balanced and all that, but I'm not getting, I don't know if I'm calculating the enthalpy wrong.
Are you on part C?
Yeah.
Okay. This one's tough, actually. So here's what we have. I don't know if y'all have the homework pulled up. If you do, great. If not, what you have is a reaction with octane. And it says that, does it give you 5 grams, Kathleen?
5 for what, part C?
Well, just in that little blue box up on the top left.
Oh yeah, 5, sorry.
So it says during the combustion of 5 grams of octane, we're combusting octane, we're gonna release 239.5 kcal, 239.5 kcal of energy is released. So your delta H here is negative 239.5.
Oh,
So, all right. So part C, we need this information to do part C. Part C says how much energy in kilojoules is released by the combustion of 1.3 ml. So actually we don't need kcals. It also gives you kilojoules. It says, or in parentheses, that is equivalent to 1,002 kilojoules. All right, so your delta H is negative 1,002 kilojoules. All right, that's actually what we're going to use for part C. So how much energy in kilojoules is released by the combustion? We have 1.3 moles of CH. You okay, Bubba? H18. Okay. All right. Now, if what we need is a relationship ultimately. We need to relate an amount of octane to this amount of energy. But it would be much easier if we had that in moles because we were given a value down here in moles. So the first step to do this, one, is we're going to convert grams of octane to moles. Once we do that, we'll just write a relationship. We'll say this number of moles of octane is corresponding to that number of kilojoules of energy. And then we'll plug it in, cancel out moles, and convert to kilojoules. So does anybody know the molar mass of octane? Do you happen to have that, Kathleen?
not yet.
I think it's like 114, if I remember from an email, because someone asked about this problem. Molar mass of octane. We can add it up. There's 8 carbons, so that's 12.011, and 18 times 1.08 or 1.01.
Got 114.232.
114.232 grams per mole. So let's take 5 grams here and let's just convert that to moles. So we're gonna cancel grams, 114.232 grams for every 1 mole. And how many moles do we get?
.044.
0.044 moles of C8H18. All right, now we're going to write a relationship. So step 2 is we're going to use this relationship to go from moles to kilojoules. It's a K. So the relationship we're going to use there is that this many moles is related to the amount of energy with that equation. Okay, because the problem tells us during the combustion of 5 grams of octane, 1,002 kilojoules of energy is released. So 5 grams of octane is directly related to 1,002. It produced 1,002 kilojoules of energy. So we can say in moles, that is 0.044 moles is equal to -1,002 kilojoules. And that's what we're going to plug in now. With our starting number. So our starting number is right here. I'm trying to shrink it down a little bit. Okay. We're going to start right here. We're going to plug in this relationship next so that moles cancel out. So 0.044 moles of octane will give us 1,002 kilojoules. So moles of octane will cancel, and you should get a number in kilojoules of energy. Okay. So again, what we're doing here is we're taking whatever information they give us about the reaction, and we're relating that to an amount of energy, and we're using that as a conversion factor. We did it in the dry lab, number 4, part C. That was exact same style problem. And I want to say somebody else asked me another question similar. I can't remember if we worked on similar, but this is the exact same thing as number 4C in the dry lab. Different reaction, of course, but same concept.
Okay, thank you.
Questions on any further parts, D or E?
Yeah, if you want to do D, that would be awesome.
Yeah.
I think it's the same type of thing. Part D and E look very similar, same at least thought process here. Part D says how many moles of octane must be burned to release 547.6 kcal. How many moles of octane must be burned to release? Okay, so we have, this time we're starting with energy. So 547.6 kcal, and we want to know how many moles of octane. So we're trying to convert to moles. All right, now we have a relationship between moles and kilojoules. And we know that these numbers are equal, okay? It said it produced 239.5 kcal or 1,002 kilojoules. So those numbers are actually equal. So the way we can write this number of moles equals that many kilojoules, we can also write that many moles equals this many kilocalories. So I'm just going to rewrite a new relationship. The relationship we need is the number of moles we calculated, 0.044 moles of octane produces -239.5 kcal. So we're just going to use this cancel kcals, convert to moles. So it would look like this, 547.6 kcals. I want to cancel kcals, so I'll plug in the 239.5 here for every 0.044 moles of octane, C8H18. Is that a ring pop, Anaya? I have not had a ring pop since I was probably like 8 years old.
I got it in my bag yesterday from the fall fest going on.
That is amazing. That's awesome. Nostalgic. Trying to think about what candy is most nostalgic for me. I love chocolate candy. I'm not like, my husband would prefer all the like fruit candy, like Skittles and stuff. I think growing up, one candy that I haven't had in a long time. Did anybody ever used to eat that brittle? It was like white and black colored. It was like a toffee brittle type thing. I don't remember what it's
Yes.
called though. And they're so good. They're wrapped in a clear package, clear little plastic.
I saw those at Michael's the other day.
Oh, really? I forget.
Flashback.
We used to eat those. Pop Rocks, Dakota said. You like Pop Rocks?
I prefer fruity candy too, because chocolate gives me heartburns.
Oh man, that's
Yeah.
devastating. Have you ever had the chewy Jolly Ranchers? They have little chewy
Yes.
Jolly Ranchers. Those are dangerous. Those are dangerous. All right, part E, I think is very similar. It's just instead of stopping at moles, well, actually you're starting with grams. So you need to take that number of grams of octane. So it gives you, for me, it tells me 19.9 grams. So for part E, I'm running out of space here. Part E, it told me 19.9 grams of C8H18, and we want to know how many kilocalories are released. So first, we have a relationship actually directly from, this one's much easier. We have a relationship directly from grams to kcals. If you read that first part of the problem in the blue box, it tells you for every 5 grams of octane, you're going to release it's got to be negative because we're releasing 239.5 kcals. So you just pull that information directly from the problem. That's for part E. And although when you type in your answer, because the question innately says how many kcals are released, I might have just misled you. It's asking for how many are released. So I think it might just want the number here. The fact that it says released indicates this, what we would be indicating by the sign if we were just writing the delta H. So I think you're just going to put in the negative or the absolute value there since it says released. Right, Joel? Sorry, guys. I normally wouldn't have a baby here, but he is, honestly, I think he's real tired. He's just not giving up the fight. Any other questions? It does make doing chemistry more fun though, right? I know that can't be all y'all's questions. Surely not. We've been going for an hour though. So if y'all's brains are tired, I get that.
I have a question on the lab on 3B. The third question, it asks if your delta H is considered a reactant or a product. I haven't calculated anything yet, but do you get that from if your reaction is exothermic or endothermic?
Yep. If your delta H is negative, and you have an exothermic reaction in that case, that means heat was produced overall. So heat's a product. Your delta H is a product. If it's endothermic, that means overall more energy was absorbed than released. So overall, there your energy term is a reactant.
Okay.
Good deal. Any other questions? Well, I will, I guess I don't know who's going to want to sit and watch this, but I will make this available to students if they want to watch this. Maybe it would be helpful. Well, I think we're about out of time because the little man here is letting me know it. If there's no other questions, then y'all have a good one. Thanks for joining. And
Thanks for having this.
absolutely. If you have any other questions, just shoot me an email. Okay, bye.